Hey guys, today we're going to go through, hopefully in less than 10 minutes, as much as I can very quickly, uh, a fully fledged project that deals with the natural language processing techniques such as vectorization, transformers, convolutional neural networks, and data validation, and so on. So the basic idea is this is a resume categorizer. So we have a resume, we input the text, and we just want to know what category it falls under. So the first thing, we use the data set. This is the largest data set that I could find online that has raw data. There are other ones that were larger, but they were pre-processed or tokenized, and I wanted to find something that is raw just to apply the pre-processing steps to it from scratch. So this is around 2,500 or 3,000 entries, which is actually very small. It's not that big, which will come later to us further. We will reference this again at the end. Visualizations, we just have simple visualization at the beginning just to get an overview of the data. We have the resume length. So here we can see that the frequency, the highest frequency is of length around 7,000. So you just get an idea how long the resumes are. So usually most of them are more than 5,000, less than 10,000, they're somewhere in between. So we just have an idea. And here is the same but separated by category. So we can see that each category almost have the same length of characters, but there are some outliers, as you can see. This is a box plot, so it just keeps the interquartile, but we can actually see the individual outliers in the construction, for example, and so on. But we can see that most of them, they're not hugely different, but there's a lot of variance. And here we can see the most frequent words. This is very useful because we haven't yet pre-processed the data, so we can see that, okay, we need to do something about this. We have a comma, the most frequent, and period too, which these are a bunch of stop words and a bunch of just punctuation. And the next one gets us a closer idea of what we want to end up with: bigrams toward phrases, city, state, company, city, customer service. So this is kind of what we want to see, not the previous comma and to, from. So how to achieve this? We just perform some text cleaning. We remove all the stop words, we remove all the HTML tags, we just remove all the special characters, everything, the white space, just to clean the data, and we perform some unit tests on it. And here we set up the vectorizer that we will use later in the TF idea vectorizer, which is the baseline model, as I call it here, because it's the simplest model. And here we set up the embeddings for the glove modified transformer. So here we have a convolutional neural network, and here we have a transformer, a simple transformer. Here we have the glove, which is just a transformer that is embedded with the glove. What the glove does is basically, it's a bunch of pre-trained data set with its own parameters, and it helps us have more context about the world. So I only train about resumes, but there might be some other things. Maybe some hobbies. Someone is talking about how they like to play music or guitars or whatever. So we need to have more context about it. That's usually not within the resume data set that we have. So this is a way to actually improve our data set. And here we have the robust model, which is also a transformer, but it has regularization, early stopping. These are all techniques to avoid overfitting and just ensure that we have higher recall, not just higher accuracy, and just simply reproducibility of the result. We don't want to memorize the data set, which is very interesting because we'll come up to that later. And this is a baseline, very simple. We just have a baseline that relies on a vectorizer. That's it. How the vectorizer works, it just converts the strings into a vector and a bunch of integers, and depending on the frequency of the specific words, it can determine whether or not it is within this category or this category, etc. It has no context whatsoever, it has no semantics. Here we have some cross-validation techniques. I used the stratified k-fold. K is just a constant. I used 5 as the value for k here. And how it works is, instead of having 80% training, 20% testing, we actually do 80% training, 20% testing 5 different times. We change the 20% each time. So we have 5 different views of the dataset. So we don't have a lucky strike or some sort of bias depending on which 20% we chose. So we have 5 different point of view to the same dataset. So this also ensures we avoid overfitting. And we can see here the visualization for this. The highest accuracy is the convolutional neural network, and the glove, which is the transformer with the embedding, and baseline is the lowest accuracy, which is expected, but again, will be interesting very soon. So we just here do further metrics. We can see here the accuracy for the baseline, F1 score, AUC, which is the area under the curve, which is also a metric for determining how close it categorizes the whole thing based on graphing each entry with its Y value, which is the target value, and the better it expects, the higher the area will be. And if we go up here, we can see the convolutional neural network. This is all the metrics for it. And here we have just a general validation accuracy comparison. We just confirm the over each epoch, which is another word for loop. So each loop, how much we are changing in accuracy, and the higher we improve, the better from the validation point of view, and the loss is just the reverse of that. So we can see again, convolutional neural network is the highest here, and it's the lowest here. So here we could just stop. We can just say, okay, we figured it out, convolutional neural network is the best. But when I actually did this practically, I just tried some resumes just from random things like this website, or just did some random sources. It wasn't actually that accurate. So I tried to simulate a real different data set. So it has to be a different data set because we already had training on the data set, we already had testing, we already had a validation data set, we already did all of that. But still, we're facing an issue. So I just made a synthesized data set, which is not a good idea to just train your model on, because it's not a good classifier of what is out there, what represents the data. But I just try to use it just to have an idea about, okay, how would it look like if someone with their own resume submitted this. So I just synthesized a bunch of keywords based on each category, and we compared the real test data versus the synthetic data. You can see the convolutional neural network and the transformer, the glove, the robust, all of them, they have high accuracy. But when they come to the synthetic generated data, they all fall behind at a point where the transformer and the robust, basically, they perform a random guess. This is just 1 out of 24, about 4%, which is the random guess. So if you just blindly guessed, it would be as good as the transformer or the robust. Why does that happen? Because the way the model works is that it has some sort of context about it. but it finds words that are not within the context. So it just has an educated guess. Okay, I'm pretty sure this is gonna be it because this is the most universal of them, and it chooses a random category as that. So we can see that each one has would have a very biased. Like here, it shows sales. It just shows that because this is new to the model. It didn't see it before. It's like, I don't know what this is. I'm just gonna guess. So this is called class. A class destruction. Class collapse, sorry, not class destruction, class collapse. Class collapse is the term for when it actually just falls apart and it starts guessing. But we can see that the simpler model, because the way it works, it just finds, okay, I see that this keyword that I already know is here, and it happened this amount of times, it's probably going to be this. So it had the best out of them. All of them look confused, but the simple model looks not the best, but still looks decent. And here we have a simple application interface within the Colab environment itself. And here, this is the result of it, but I want to actually show something better. We can export the parameters of the model, and we can use just the application, a web application that I created here, and it's hosted here. We can just refresh this just to see it in action. And you can actually upload a PDF as well, but I don't have a PDF of my own right now to try. So we're just gonna try this. And this is based on the simple TF-IDF vectorizer, which is the simplest of them all, but in real scenarios, it has the highest success rate. So here we can see HR, and this was actually HR, yeah. So this is basically an overview of the whole thing. I hope I just put into your mind that when choosing a dataset, you need to be sure how big it is. The smaller the dataset is, the simpler the model should be, because larger models rely on huge context, and 3,000 is not really that huge. Actual models have millions of entries, so you can't just rely, okay, I did some tests, I should rely on this. You need to do more advanced benchmarking to actually figure out what is the best model here, what would be the most reproducible result here in real life scenarios. And I hope I was able to clarify this project and give you a whole idea about how you can build a natural language processing project with small database or a huge database. Depending on that, you should shift your priorities.